Hello, my name is Matthew Corbett, and today I will be presenting creating an efficient electromagnetic model to replace current inadequate magnetic rail designs. Ever since I was young, I've been interested in the military, and I became even more intrigued when I learned about the Navy's railgun. I was very interested in it until recently, when I learned that the development of the railgun had dramatically slowed down. It was then that I learned of the coil gun, which is a more effective alternative. The problem with this is that currently electromagnetic coils are used much less than electromagnetic rails, because rails are much easier to build on a large scale. The simplicity of the rails is easier to build, however, it provides less power over a coiled structure. My design goal in this experiment would find the most effective model of electromagnetic coils, and this can be found by testing the effectiveness of coils at different gauges and different lengths of coil, and this would discover a more efficient model of the electromagnetic coil. In my research, I found that magnetic fields, which are caused by an electric current running through the coils, can cause the projectile to be forced to the center of the coils and propelled forward if timed correctly. For my design goal implementation, I said that if the coil length is increased from 10 to 15 and 20 centimeters and the gauge is lowered from 20 to 15 or 10, then the coils of the lowest gauge and greatest length would propel the projectile further. This means that greater surface area increases the size of the magnetic field. With that greater magnetic field, force would increase, and the projectile would be propelled to a greater distance. A complete material list can be found in my research plan. In my procedure, I tested 5 trials of 3 gauges, 10, 15, and 20 gauge, and lengths of 10, 15, and 20 centimeters. A complete list of my procedure can be found here and in my research plan. My project can be shown in action here. This first graph shows the distance the projectile propels within 5 trials using a 20 centimeter wire. It shows that the average distance propelled by a 20 centimeter wire increases as the gauge increases. This is seen in the bar graphs as the average, shown in green, of the 20 gauge wire is greater than that of the 15 and 10 gauge wire. In this next graph, which is the distance the projectile propelled within 5 trials using a 15 centimeter wire, shows that the average distance propelled by a 15 centimeter wire increases as the gauge increases. This is also seen as the averages increase as the gauge increases, shown in green. In this next graph, it shows the distance the projectile is propelled within 5 trials using a 10 centimeter wire length. It shows that the average distance propelled by a 10 centimeter wire shows the average distance is not increased with 20 gauge, but is similar to the 10 gauge. An ANOVA analysis shows that the 15 gauge wire significantly propelled the projectile the furthest. This is seen as the average of the 15 gauge wire is greater than that of the 20 and 10 gauge wire. On this first graph to the left, it shows a comparison of the average distance propelled in centimeters by gauge width. It shows that the 20 gauge wire has the highest overall distance propelled. However, the 15 gauge wire's 10 centimeter distance is greater than all of the others. On the right, the graph shows the comparison of the average propelled distance using 10, 15, and 20 centimeter wire. It shows that the 10 centimeter wire propelled greater than all of the other wires in every aspect. To analyze the data, the length that the projectile has traveled from the end of the coil system to the end of the projectile was measured in centimeters. 5 trials for each of the 3 gauges and 3 coil lengths show an increasing gauge is efficient to a certain point until the length becomes too short. A decrease in length always leads to increased projectile distance. According to ANOVA analysis, there is a significant increase in the distance that 15 gauge can propel the projectile using a 10 centimeter wire compared to 10 and 20 gauge wires. A summary of the ANOVA analysis shows a p-value of 0.014878 with a significance of p being less than 0.5. This chart shows that the number of trials was 5 for each of these. The mean for the 10 gauge was 66.8, for the 15 gauge 98.6, for the 20 gauge 73.2, and the standard deviation of the 10 gauge was 11.5, for the 15 gauge was 13.1, and for the 20 gauge was 20.3. I concluded that the data did not support my hypothesis, in which I stated that a decrease in gauge and an increase in length would cause the projectile to be propelled further. I now conclude that the opposite is true, due to weaker magnetic fields caused by a weaker current and larger volumes of coiled wire. The main application can be seen in replacing railguns with coil guns on battleships, such as the USS Dewey. This is because research on railguns has come to a halt, as many problems of the railgun are showing up. An alternate application is that this technology can be used as a form of high-speed transportation, possibly in underground tunnels or tubes. The next step that could be taken in this experiment is to try to find the most efficient ratio of gauge to wire length with a set flow of electricity. Also, different materials could be tested for the projectile to try to further increase efficiency and distance propelled. A complete bibliography can be found in the research plan. Thank you.